Hello, this is our 12th and final lecture for CSCE 317 for spring 2020. Today I will be reviewing all the information you need for the final exam. As indicated in the revised syllabus, the final exam carries a weight of 20%. The original scheduled time was May 4th from 12:30 to 3 o'clock, but we will make the final exam available on Dropbox from 12:30 p.m. on May 4th, which is the original start time, to 12:30 p.m. on May 5th. So it'll be available for 24 hours. Once you start the exam, you must complete it within 2.5 hours, and there is only one attempt. Now, this exam will not ask you anything about the ATmega 328P because we intended for that only to be used for the lab part of the course. So the exam will only cover conceptual material from the course. It will be, and I will, in this lecture, I'm going to enumerate everything you need to know for the exam, all the topics. The book will be open, the exam will be open book and open internet. However, our academic honesty policy for the exam is that communication among 2 or more current students where any participant is taking the exam or any participant has not taken and another participant has taken will constitute an honor code violation. So you can, in other words, you can talk before you take the exam, and you can talk after. Don't talk to each other during the exam, or don't talk to someone who's already taken the exam if you have not. Or if you've taken it, don't talk to anyone who has not. Okay, so topic 1 for the exam is bit twiddling. This would be, so bit twiddling is manipulation of individual bits within a larger data object, data value, right? So in this case, the word size is 8 bits for all the projects we did in this course. So how do you manipulate, how do you read and change individual bits within an 8-bit byte? That's bit twiddling. So for example, if I want to set bit 2, which would be the 3rd bit from the right, or the 3rd least significant bit, if I wanted to set it to a value of 1, so I would first consider an 8-bit value of just 1, meaning that it would be all zeros except for a 1 in the rightmost position of the byte. I can then shift that register 2 bits to the left, or shift that value 2 bits to the left, rather, which will position the 1 bit into bit position 2. And then, if I have a value that I wanted to set to set bit 2 to 1, I could then OR that value with the 1 shifted by 2 bits to the left. So it's a little hard to tell from the slide here, but these are bars, these are OR symbols, bitwise OR. So the top value represents the value that you want to set the 1 in bit position 2. The bottom value here is just the value of 1 shifted 2 bits to the left, and then I do a bitwise OR between those, and it will then set the corresponding bit to 1. So note, originally the value had a 0 in bit position 2, and after I perform the bitwise OR, the bit is now, that 1 bit is set to 1, right? So basically, this represents the line of code val equals val OR bar 1 left shift by 2 bits. Now in C and in Java, the shift operation has lower precedence than the OR operation, the bitwise OR. So you have to be careful that you enclose the 1 shift left by 2 bits in parentheses. Right? So you want to make sure that the shift happens first, the bitwise OR happens second. On the other hand, if I wanted to set, say, bit 3 to the value of 0, I would again start out with the value of 1 in 8 bits. And then again I would shift it, in this case by 3 bits, because I want to set, I want to make a change to bit 3. And then I would perform a bitwise complement with this tilde, which will change the zeros to 1 and 1 to 0. So I'll end up with a value that is all 1s with a 0, except for a 0 in bit position 3. So if I start out with the same value I had before, I can then do a bitwise AND with this value, where all the bits are 1 except for bit position 3, which is 0. And that will effectively change bit position 3 to 0. So this is equivalent to the line of code val equals val and tilde 1 shifted left by 3 bits. Now, keep in mind that if the bit value in position 3 was already a 0, this won't change that. This operation just ensures that the bit in position 3 is 0 after this operation happens. Likewise, when I set a bit to 1, if the original value already had a 1 in bit position 2, then this operation, this statement would have no effect. Right? Okay, so make sure you're comfortable with doing this for the exam. Setting a specified bit to 0 or to 1 in a variable or a register. Okay, how about shifting or isolating certain bits? So if I want to isolate bit 3, I want to read what the value of bit 3 is. I don't want to set bit 3, I want to read what bit 3 is. Then I could shift that value 3 bits to the right. Now in this case I'm showing 1 bit shift at a time. So the value, obviously the zeros get shifted in the left hand side when I shift to the right, and so this shows 3 single bit shifts to the right. Of course, in a language like C, you could do you wouldn't need 3 separate statements to do this. You could just shift by 3 bits instead of by 1. But what this does is positions bit 3 into the least significant bit position, and so then I could do a bitwise AND with the value of 1, which will clear all of the 7 bits to the left of 1, and will leave just the bit position 0, the value of bit position 0 left over. So this will result in the value being all zeros or all zeros with a 1. So in other words, the bitwise AND essentially masks away all the bit values that I'm not interested in, and leaves only the least significant bit left over, which originally was bit number 3 in the original value. So this line of code, which I forgot to note here, would be val, or forgot to type in, it would be val equals val shifted to the right by 3 bit positions, and close that in parentheses, and then bitwise AND 1. So that would set val to be whatever the value of bit position 3 was in val. So the new value of value would be the bit 3 of the original value stored in val. So this is one way to read a specific bit position in a value. Okay, so let's switch topics now and talk briefly about interrupts. This is something that we haven't covered since earlier in the semester. We talked about these obviously in the context of the Atmel 328P I did some demos in class where I showed you how to use interrupts. We never, unfortunately, got to a project where you had to use interrupts. It was always an option. But the concept of an interrupt is something that you should know for the exam. So basically the idea is that if we have a signal called int0, that is a bit, 1-bit signal, but it is a signal that is designed to interrupt the CPU. The way in which you interpret that signal depends on the way that the CPU is configured. So one way to do it is using a rising edge triggered interrupt that would wait for a low to high transition of the interrupt signal to interrupt the CPU, whatever it's doing. It will temporarily stop doing that and then automatically branch to, or I should say jump to, an ISR, an interrupt service routine. And then when the interrupt service routine is finished, the CPU will go back to doing what it was doing before the interrupt occurred. The advantage of an edge-triggered interrupt is that there's after the interrupt routine is complete, there's no risk of triggering another interrupt, even though in this case the interrupt request is still high at the time the interrupt service routine finishes execution. And this could happen if the peripheral doesn't necessarily know when the interrupt service routine is finished, or even if the CPU has seen the interrupt or acknowledged the interrupt. There's no acknowledgement mechanism in this case shown. In some cases there is an acknowledgement mechanism, but in this case we're assuming there is not, and so the rising edge triggered has the advantage of allowing the CPU to respond to the edge, only the rising edge. On the other hand, a level triggered interrupt, and it could be level high, level low, just like the edge triggered interrupt could be rising edge or falling edge. But in this case, if we have a level triggered interrupt where the level that triggers it is the high level, is the 1, you can run into this potential issue where when the CPU returns from the interrupt service routine, it will return to discover that the interrupt is still high, in which case it may go back and have to service that interrupt again, which may or may not be what you want. It's probably not what you want, because the whatever caused this interrupt there's probably only one thing that caused this interrupt to be high for the duration of this pulse, right? So just make sure that you are that you understand edge triggered versus level triggered interrupts. Oh yes, and yeah, so it's the rising edge that triggers the jumping to the interrupt, and in this case it is the rising edge, the high value of the IRQ or the interrupt pin that causes the CPU to service the interrupt. Okay, next topic is pulse width modulation. This is again something that we talked about earlier in the semester, and this is something that you did implement in lab 2, right? Or was it lab 1? Lab 1, or I don't remember. Sorry, my memory is shot. But anyway, pulse width modulation is a way to implement an analog value with a digital pin. So a PWM signal, a PWM pin, would be periodic, which means that it follows a repeating pattern with a fixed frequency. So if you measure the time from rising edge to rising edge or falling edge to falling edge, that is the period. The period for a PWM signal is generally held constant. And then within that period you have a time. So from rising edge to rising edge there is a time, there's a portion of that period where the signal is high, and there's a portion where it's low. The portion where it's high is the duty cycle, so this shows a 10% duty cycle where the signal is high for 10% of the period. And you can scale that all the way up to 100%. So because the signal is 1 or 0 and is 1 for a certain percentage of the duty cycle, if you look at the average value of that signal, then the average value would be a voltage, the average voltage of the value. Because remember, 0 is going to be 0 volts, and 1 is going to be whatever the power supply is. In our case, it was 5 volts. Or 3.3, whatever the voltage of the PWM signal is, but the average voltage is going to be the power supply voltage multiplied by the duty cycle percentage. So if this is, for example, a 5-volt signal and there's a 10% duty cycle, then that would be an average voltage of 5 volts multiplied by 0.1, so half a volt, or 500 millivolts. So that's a way that we can that we can achieve basically a continuous voltage value for a pin, as compared to just the 0 or VDD values that you normally have with a digital pin. Of course, it requires that you have something that can interpret the voltage as an average. Which, with an LED, for instance, an LED brightness will generally show up as kind of the average of the signal. But on the other hand, if you were trying to do something like audio, then you would need to also add in a filter to reduce any kind of noise that you would get from doing PWM into a speaker. Okay, all right. So the next topic is bus protocols. Buses can be, well, first of all, bus is kind of a little bit of an outdated term. What we're really talking about are system level interconnects. So how do chips, different chips in a system communicate with one another? In our case, we're talking about a CPU wanting to communicate with peripherals, which peripherals are I/O devices, like sensors, storage, that kind of stuff. So bus protocols can be asynchronous, meaning that they're not clocked. There's no clock signal as part of them, or they can be synchronous, meaning that we include a clock signal. In this semester, we covered one asynchronous bus protocol, which was UART, and we covered 2 synchronous bus protocols, which were SPI and I2C. Now there is a point here that's a bit confusing. UART stands for Universal Asynchronous Receiver Transmitter. So obviously UART is asynchronous because the A in UART stands for asynchronous. There's also USART, which is an option in the Atmega 328P. USART is a way to do sort of a hybrid between UART and SPI, and so, but everything we covered in this semester, if we did refer to it as USART, we were only using it as UART. So please, don't get confused by that. I updated the slides, the title of the slides, to UART, so I will refer to it as UART, not USART. So again, we have UART, no clock. SPI and I2C have a clock. So UART is asynchronous, and those SPI and I2C are synchronous. And we didn't, like I said, we didn't explicitly use USART. All right, so UART has 3 wires that form the protocol. UART involves just 2 endpoints. There's only 2 devices that can communicate with one UART channel, or one set of UART wires. There's 3 wires. There's the transmit wire, there's the receive wire, and there's the ground. And the transmit and the receive are crossed over. So the transmit on one device is connected to the receive on the other, and the receive on one device is connected to the transmit on the other, and the ground is shared between the 2. There is no clock signal as part of UART, because to use UART, both sides of the connection have to pre-agree on a baud rate or a bit rate that the channel will use. And then each one will use their own internal clock at that rate for both sending and receiving data. The nice thing about UART is that it's simple and it allows for bidirectional communication, so both sides can communicate simultaneously. So a UART, when you do when you transmit data with UART, there is this notion of a start bit and a stop bit. Start bit marks the beginning of a transmission. Stop bit is the end. These are performed independently on both the receive and the transmit channel. In fact, you could just have one side. You don't even need to have both transmit and receive. If you wanted to make a unidirectional UART, you could just have one of the two bits, the two directions. That's not a problem. So with a UART though, whenever the bus is idle, not being used, it's logic 1. So the start bit is pretty straightforward. It's whenever you want to start a transmission, you pull down, meaning that you set the wire to 0 for 1 bit time. So if your baud rate is 57,600 or 9,600, whatever the case may be, let's say 57,600 bits per second, your start bit would be marked or denoted or registered as driving the bus low, the pin low, your transmit pin low, for 1/57,600th of a second, and that would indicate to the other side that you're about to send data. So at that point, you just send the data in least significant to most significant bit. So bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, bit 8. And those are all done in consecutive slots. So that would be, you would divide up the time in 1/57,600th of a second periods, if that was your baud rate. And then you would then just drive the bus 1 or 0 depending on the bit that you're sending. And then the stop bit is when you drive the bus to logic level 1 for 1 over the baud rate amount of time to indicate that you want to stop. Right? So you can optionally also have a parity bit, and again, this is something that both sides would have to agree on and be consistent with from the beginning. So a parity bit is optional. Parity bit allows for error detection. So if you have odd parity, the parity bit, which would come after the data bits, would be logic high if the number of bits in the byte were even. Wait, that didn't make any sense. If they're even? I thought it was odd parity. Why would it be true if there's an even number of 1 bits? Well, it's because if there is an even number of bits and the odd parity bit is high, or the parity bit is high, then if you count the number of 1 bits in the data, the data word, the data byte, the byte that you're sending, in addition to the parity bit, the total number of 1 bits would be odd, right? Because there would be an even number in the byte that you're transmitting, and plus there would be an extra 1 set to 1 in the parity bit. So likewise with even parity, the parity bit will be logic high if the data byte that was transmitted contains an odd number of logic high bits. So you can think of it this way: the parity bit is designed to force the total number of 1 bits in both across both the byte and the parity bit to be either even or odd. Right? And as I mentioned earlier, the baud rate is the rate at which the bits on the line are transferred, right? But the baud rate, obviously, is not necessarily the rate at which you're sending data, because the baud rate indicates the period for each bit on the bus, which includes overhead bits like the start, stop, and parity bit. So the baud rate is an indicator of how much time is given to one bit slot on the bus, including, which also includes those slots also have to be allocated towards the start and the stop and the parity bit as well. Okay, so here's an example of the form of problem you'll likely see on the exam. In this case, we have a UART transaction with 5 data bits, with the least significant bit transmitted first, an odd parity bit, and 1 stop bit. So to read this, you can, the first bit position is the start bit, and well, you can assume the first bit slot here is the start bit, and then following that should be 5 slots for each of the data bits from least significant to most significant bit. So as shown, we have 0, and then working away from least significant to most significant, meaning from right to left, we have 1, 1, 1, 0. So 0, 1, 1, 1, 0, and the number of 1 bits there is 3, which is odd, so we'll leave the parity bit 0, or we'll drive the parity bit 0, and then we have the stop bit there. On the receive side, you have 0, 1, 0, 0, 0, and that has an odd number of 1 bits, and so the parity bit there is set to 0, which is correct. And then we have the stop bit. So we may ask you, ask you if the stop bit, if the parity bit is correct, or we may ask to, just to Here's an example of the type of question you'll see on the exam. There's a waveform here for a UART transaction that consists of 5 data bits with the least significant bit transmitted first, odd parity, 1 stop bit. So if the question were to give the 5-bit word that is transmitted and the 5-bit word that is received on this channel, then you would start on the left-hand side. You assume that the first bit slot, and the slots are denoted here with these dotted lines. The first bit slot would be the start bit, followed by 5 data bits, least significant bit first, meaning that if you were writing them down, you would start at the right and work your way to the left. So we have 0, 1, 1, 1, 0, followed by the parity and stop. So 0, 1, 1, 1, 0. From right to left is 0, 0, 1, 1, 1, 0. Sorry. So from right to left, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0. Again, we've got a slot for the start bit and 2 slots at the end for the parity and the stop bit. So we have 0. Oh, very cool. I like it. Thank you, baby.
Thank you.
I like that, babe. Okay, so here's an example of the kind of question you may see on the exam. The question shows the waveform for a UART transaction. We may ask you to give the word that is transmitted and or received over the channel, or we may ask you if the parity bit is correct, or we may give you the parity bit and all but one of the data bits and ask you to fill in what that data bit is. But just to give you an idea how to read this, you are going to read the waveform from left to right, and you can assume that the first slot, and all the bit slots are shown, by the way, with these dotted lines. The first slot is going to be for the start bit. So you've got a start bit on the left hand side, followed by 5 slots for data bits, followed by 2 slots for parity and stop bit. So we want to read the 5 bits starting with the second bit on the left, and because it's least significant to most significant, we would write those bits down from the right to the left. So for example, in this case, the 5-bit word that's being transmitted would be a 0, 1, 1, 1, 0. And again, notice I wrote that down from right to left. Now, if this had said most significant bit first, which I think would be non-standard for UART, but you know, we may specify that, then you would write the bits from left to right. But because it's least significant bit first, we're writing the bits down from right to left. Sorry, most significant would be left to right, least significant would be right to left, right? So 0, 1, 1, 1, 0. And then the parity for this is a 0. Is that correct? Well, there's an odd number of 1 bits. So while the number of 1 bits is odd, we would still set the parity bit to 0, so we could ensure that that number remains odd, right? And then that's followed by the stop bit on the right. On the receive side, we will have the start bit followed by a 0, 1, 0, 0, 0. Sorry. Yes, that's right. And then there's an odd number of 1 bits there, and thus the parity bit is 0, just as it was above, and then the stop bit. In this case, we have 7 data bits, least significant bit first. So again, we're going to be writing these bits down from right to left. But this time there's no parity and there's 1 stop bit. So you have to be careful because there's only 1 stop bit. There's only 1 bit at the end, you know, beyond where the data stops. So as far as the words being transmitted on the transmit side, we're going to have the start followed by a 0, 0, 1, 0, 1, 0, and then another 0, even though that slot is where the parity bit would be if we had parity, but we don't, and we should have 7 bits there. 1, 2, 3, 4, 5, 6, 7. That's correct. There is an even number of 1 bits, and well, it doesn't matter because we have no parity, so we don't have to worry about that. And then for the receive side, we have the start followed by a 1, 1, 0, 1, 0, 0, 1. It should be 7 bits. 1, 2, 3, 4, 5, 6, 7. Yep. And so those are the words being, that's the word rather being received. Okay, so that's UART. SPI is the second bus protocol that we covered. This is a master-slave type of protocol. So in the case of UART, the UART was a point-to-point. So you just had transmit and receive, and so whoever, you know, and you would have a crossover in between. So if I'm transmitting, that signal would go into the receive side on the other side of the channel, and I could initiate a transaction with the start bit, but likewise the other side could also initiate a transaction as well. So in that case, both ends of the link were sort of treated equally. They both behave the same way. SPI, though, is a master-slave interface, meaning that the protocol is different depending on whether it's the master side or the slave side. So SPI can have one master and one or more slaves. The SPI bus contains 4 wires, for signals, 4 pins. There's a clock, which is sometimes called SCLK, S clock, or sometimes just SCK. I usually just have, I denote it as SCLK. Then there's the MOSI, which is the master out, slave in, MISO, master in, slave out. So those are kind of analogous to the receive and transmit pins of UART. And then you've got the slave select, which is the way in which the master activates the interface on the slave side. Now normally the clock is idle, meaning that it's not alternating, it's not periodic, it's not pulsing, it's just flat. The SS signal is active low, so when the SS signal is not activating. Oh, and by the way, SS is slave select. That can also be a chip select, sometimes called chip select. But it is active low, meaning that it's normally high, and when you want to use it, you would drive it, the master would drive it low. That would activate the slave on the other side of that wire. There's also some parameters associated with the SPI bus, or a given SPI bus implementation or deployment or instance. There's the clock polarity C-pole, which defines the idle state of the clock. If C-pole is 0, that means the clock is 0 when it's not being used. If C-pole is 1, it means the clock is 1 when it's not being used. This is important because if C-pole is 0, that means the first edge of the clock that will happen during an SPI transaction is going to be a rising edge. Well, likewise, if the C-pole is 1, the first edge would be a falling edge. And then there is CFA, which stands for clock phase, and that is what determines when data is read by both the master and the slave with respect to the clock. So if CFA is 0, the data is to be read on the first clock edge, whereas if CFA is 1, the data is read on the second clock edge. So I'll show examples of that soon. Now there's some terminology that can get a bit confusing here. An SPI exchange is when 8 bits are exchanged between the master and slave. So it turns out that with SPI operations or transactions, anytime you do an SPI communication, you're always exchanging bytes. So what that means is for every byte that the master sends, the slave also sends a byte back to the master. That can be confusing because you don't always need to do that, but you have to do it anyway. So that's an exchange, and that happens in units of 8 bits. Okay. Now an SPI transaction defines all of the exchanges that take place while the slave select is asserted. So what that means is the master can drive the slave select low, and then there can be 2, 3, or 10, or 20, or 100 of the exchanges that happen within that transaction. So the transaction are normally associated with read or write operations, and in either one of those cases, if you're doing a read or write, you have to do at least 2 exchanges. The first exchange being the address, and then subsequent exchanges matching up to the data that corresponds to that address, whether it be a read or a write. So here's an example of, or this is actually a general SPI read operation. So in this case, we're showing 2 exchanges. How do we know there's 2 exchanges? Because there's 16 cycles of the clock inside of here. from the time that the chip select or slave select gets asserted by driving it to 0 to the time that it's deasserted by driving it back to 1. So we can count the number of rising edges, for instance, in the clock. And notice that this is SPC as opposed to S clock. This is yet another abbreviation for the clock in SPI. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 rising edges. There are 16 clock cycles. Because 16 is 8 times 2, there are 2 exchanges. You can see that the STI, which is yet another name for MOSI, master out, slave in, is shown to be changing 16 times. So there's 8 bits that are being sent out on each of the 2 exchanges from the master to the slave, and the slave is showing sort of a floating MISO. It doesn't have any output for the first exchange, and then it sends data on the 8 bits of data on the second exchange. You'll also notice that in the first exchange you have R, W, and MS, and then 85 down to 80. In this case, RW is the bit that signifies this transaction as being a read or write. So if read is 1, write is 0, as indicated by the bar above the write. So if write is 0, then that's means it's a negative logic. And then there's MS. MS stands for multiple or single. In this case, if that bit slot is 1, then it will be a multiple, meaning that you'll be reading or writing more than 1 byte. And then we have 6 bits of address that follow. So in this case, this looks like it's a read operation, even though the values of these slots are not shown, because we have the slave sending 8 bits back to the master. But what's odd about that is the master is also apparently sending 8 bits during the exchange, in which normally it would be idle waiting for data to come back from the slave. So this diagram is a bit confusing. But also note that the slots, the significance of each of the slots in each of the transactions depends on the application. So this is not standardized. So I may have a chip or an application where the least significant bit of the first exchange is the read or write flag, for instance, right? So these mappings of these bits are up to the chip, the pairs of chips that you're using when you use this, right? So this shows, one transaction again is the time that the chip select is asserted, and then we have 2 separate exchanges. We have the first exchange is where the master is sending an address. The second exchange is where the slave is sending back a byte of data in exchange in response. During the first exchange, the slave doesn't have anything meaningful to send back to the master. During the second exchange, the master normally would not have anything meaningful to send to the slave if it were a read operation, although according to this diagram it looks like it is sending something. Okay, this would be a multiple read, where in this case we have 3 exchanges, the first exchange being the address and the next 2 exchanges corresponding to 2 bytes being read, starting from the address specified in the address exchange. Okay, so here's an example of an SPI exchange. Now notice that we've got 1 transaction here because the slave select has only 1 falling and 1 rising edge. And if we count the number of cycles, we've got 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 cycles. That means only 1 exchange. So unlike the 2 diagrams we just looked at, this is a 1 exchange transaction. CPOOL is 0, meaning that the clock is 0 by default. You can see it is 0 there at the beginning. CFA is 0, which means we're going to read the data on the first edge of the clock. Well, the first edge of the clock is very easy to identify. You just start from the left and you find it there. So there's the first one. So if we look at MOSI, we can see that the data being sent on MOSI is a 1. Matches up with the rising edge of the clock. 1, 0, 1, 0, 0, 0, 1, 1. right? And it's most significant bit first, so if we were writing this down, we'd be writing this one down from the right to the left. So MOSI, the master, is sending, again, it would be 1, 0, 1, 0, 0, 0, 1, 1, and then MISO is the data coming back to the master from the slave, and that would be 0, 0, 0, 0, 1, 0, 0, 1. So you just follow the first rising edge, and then each rising edge after that, and you just, at each edge, you just look down to see what the corresponding value of MOSI and MISO are. Here's another example. In this case, CPUL is 1. That means clock starts out as 1. CFA is 1, which means in this case, we don't look at the first edge of the clock, which would be falling edge. We look at the second edge with the rising edge. So in this case, the second rising edge of the clock is the rising. Sorry, the second edge of the clock is a rising edge. And so if we look down from there, we can see that MOSI is sending, the master is sending 0, 1, 0, 0, 0, 1, 0, 0, and MISO is sending 0, 0, 0, 1, 1, 0, 1, 0. Now in this case, though, least significant bit is first, so if I were writing this down, I would be writing this down from right to left this time. Okay, but again, this is a one exchange transaction. However, I can have more than one exchange, so in this case, I have a longer transaction, and I had to shrink this waveform down in order to fit it on the slide. There are 16 clock cycles in it, so in this case, obviously there's a 2 exchanges being done. The master sends 2 bytes to the slave sends 2 bytes back to the master. And if we told you, for example, that in this case, say the first bit denoted a read or a write, and the following the first bit in the first exchange from the master was the read or write bit, and then the following 7 bits were the address, then in that case, let's see, how would I decode that? Well, CPUL is 0, so the clock starts out as 0. CFA is 0, so I'm going to start with the first. I'm going to read on the first edge of the clock. So the first bit then from the master is going to be a 1. So let's say, I don't know what that means in this case because I didn't specify, but let's say 1 in the first bit position in the address exchange corresponds to a read. That would mean that I'm doing a read because the first bit in the first exchange is a 1, and then the address would be the next 7 bits. So 0, 1, 0, 0, 0, 1, 1, right? If I counted that right? That's 1, 2, 3, 4, 5, 6, 7, 8. Yes, okay. So I'll count forward again. 1, 2, 3, 4, 5, 6, 7, 8. So that's the first exchange. So the second exchange is now going to be the slave would be responding if it were read. So and as you can easily see, the slave is sending back all zeros in this case. But this looks suspicious though, because if this were a read operation, you would expect the master not to send anything in the second exchange, but it is. So actually it turns out that this is most likely without, again, it's not specified how to determine whether this is read or write, but just looking from the waveform, it looks like it's probably a write because the slave has nothing to say at all to the master, yet the master has 2 bytes that it's conveying over to the slave. So this is probably a write, and if it is a write, then the first exchange would be a again it would be a 1 0 1 0 0 0 1 1, and then that would be the end, right? And the next exchange would start here, 0 0 0 0 1 0 0 1. If I counted that right? So so basically, you're dividing this in half. So the first half is the address, the second half is the word. So it looks like this is, again, it looks like it's a write, just based on the bits being sent. Okay, so in this example, this is a little bit better because in this case, this is actually specifying if the most significant bit of the address is 0, then it's a read. If it's 1, it's a write. So that gives us more information to go by. So now I can look for that first bit. So CPUL is 0, CFA is 0, CFA is 0. That means that is this the same? No, it's a different transaction. So most significant bit first, CFA is 0, so we're just looking at the first rising edge of clock, so we have a 1, so 1 in this case means it's a write, so the address of that write is starting from the left to the right, 0, 1, 0, 0, 0, 1, 1. Right? Okay, now wait a second. Let's check this out. 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the first transaction ends. This is the last bit of the first transaction. So it looks like I'm only a third of the way through that. So this is actually a 3 exchange transaction. So after sending the address, which I do after the first 8 cycles, then I have another 16 cycles where apparently the master is writing 2 bytes, which are then listed in the following 16 cycles, right? So the first byte would be 0, 0, 0, 0, 1, 0. 0, 1. I think that's right. And the second byte would be 0, 1, 1, 0, 1, 1, 0, 1. So actually, just to make sure I counted right, let's write this down. Okay, so the address would be the first bit would be just a flag saying that I'm doing it right, so that would be a 1, and then 0, 1, 0, 0, 0, and then 1, 1. That's this pulse. So that gives us a 1, 2, 3, 4, 5, 6, 7. Okay, so the address ends after this 2-bit pulse. And then word 1 would be 1, 2, 3, 4 zeros, followed by a 1, and then 2 zeros. So it's 1, 2, 3, 4, 5, 6, 7, and I need 1 more so that there's an extra 1 on there. And then the word 2 would start after this 1 bit, so that would be a 0, 1, 1, 0, 1, 1, and then 0, 1. So 0, 1, 1, 0, 1, 1, 0, 1, and 1, 2, 3, 4, 5, 6, 7, 8. That's 8 bits. And again, I wrote these from left to right because it was most significant bit first. Okay. All right. Okay. So SPI can have multiple slaves. There are 2 ways to do multiple slaves. You can either treat the slaves independently by associating a dedicated slave select or chip select wire for each slave, and then having each of the slaves all read the same MOSI. So in other words, the master will send MOSI to broadcast it to all the slaves, but only one slave will actually pay attention to that, depending on which slave was had its chip select or slave select selected, right? Or you can make them daisy chained, in which case you have you treat all the slaves as one long shift register where MISO coming out of one slave feeds into the MOSI of the next, and so on until you get to the last slave where the MISO feeds back to the master. So this is kind of a daisy chained approach. If you use the daisy chained approach, then one exchange, in order to do an exchange, you would have to, the clock would actually have to pulse not 8 times, because 8 times would only get a word from the master into the first slave and from the last slave into the master. You would need to go 24 cycles to cycle all of the slave data back to the master. It would take 24 cycles. On the other hand, in the case of the independent, you have an issue where the MISO of each of the slaves are all shorted together, which is dangerous because the MISO is an active pin, it's an output pin. And so what is the problem with that? Well, the problem is that SPI uses a push-pull type interface, meaning that the output pins of each of the devices are are either pulled up or pulled down, pulled up to VDD or pulled down to ground, meaning that they are actively driven high or low. Now, in this case, in this independent case where you have two slaves both driving the same meso, so I mean, there's obviously 3 in this diagram and there's 2 in this diagram. So the driver circuits look like this. I mean, they're basically inverters. And the problem is that if one device attempts to pull up and the other device attempts to pull down, so you've got one slave driving a 0 and one slave driving a 1 onto the same meso line, that would create a low impedance path between the power supply and ground. So it would cause a short circuit basically, and this would result in very high current flowing, which would either burn the chip up or it would drop the voltage low enough to kind of shut the system down. Either way, it wouldn't be good. So another option would be to, instead of doing this push-pull, you can use an open drain style interface, but this is actually not what SPI uses. This is what I2C uses, which is the third bus protocol that we covered in class. So in an open drain type interface, each of the individual endpoints that potentially can drive the same wire only have a pull-down transistor that can pull down the wire to ground, and then all of them have a pull-up resistor to the power supply. That way, if none of the participating endpoints attempt to pull down the signal, then the default value would just be 1. So this actually works out very nice because transistors rather have a very high off resistance, meaning that if you're not pulling down, you're actually presenting a very high impedance path to the ground, right? And then you have a 10 kilo ohm path up to VDD. So that will result in a small voltage drop here. Instead of 1, well, it'll be 1, but it won't be 5 volts, for instance. If VDD were 5, it would be by 4.9 volts, because you would have a small voltage drop over this resistor. On the other hand, if one of these guys pulls down, then you have a very low impedance path here to ground, and you will get some current flowing through this pull-up resistor down to ground, but not nearly enough to cause a problem. Maybe a 0.5 milliamp. So that's basically going to be 500 times less than you would if you had the push-pull and you had one device pull up and the other pull down. So this is what you have basically for I2C. So if we very quickly go back to SPI just to close the chapter on that, this is what I was talking about earlier. You have this potential conflict between the mesos. So the way that SPI actually solves this is, even though it's using a push-pull, it still uses, it ends up having to use this tri-state style where only one of the slaves would be actually physically would either, well, 1 or 0, depending on, 1 at most slave would be actually driving me, so the other ones would use a transmission gate or a pass gate, or some sort of way to disconnect themselves from meso. Okay, so anyway, back to I2C. So as I mentioned, I2C uses the open drain or the pull-up style. I2C is a bit more complex than SPI. It uses only 2 wires. It is also a master-slave style interface, but it's multi-master. So any device on the bus can be the master. It just needs to claim mastership of the bus. In which case it then would initiate a transaction with another device, which would then be in the slave role only for that transaction. I2C though is also only unidirectional though, so only one device can actually talk on the bus at one time, and that is an issue because what that essentially means is that the data wire, which is SDA, is going to change hands, meaning that whatever device is actually setting the SDA wire will change during the course of one transaction. So basically meaning that the device that's actually controlling SDA is changing within one transaction. So there is a start bit in I2C, kind of like in UART, except it's a little bit more complicated because the start bit is actually a condition when you have a falling edge of SDA followed by a falling edge of SCL. So falling edge of the data followed by a falling edge of the clock. Now remember that it's a pull-up, so the default, much like UART, the default signal state of these buses are both 1. So if no one's doing anything, you have a 1, except in this case it's because of the pull-up resistor. So if I want to assert mastership of the bus, assuming that it's idle, I would pull down SDA first, pull down SCL second. At that point, I should be recognized by all devices that are connected to that bus as the master. The next step is to transmit the address, as well as any flags as well. Now in I2C, the flag locations are actually part of the spec, right? So whereas SPI, the read-write bit could be any bit of the address depending on the application. With I2C, it is always the last bit transmitted as part of the address phase. Okay. Now the other difference with I2C is that we don't necessarily look at clock edges in I2C when it comes to clocking the data, because in I2C each bit is sent by setting that bit on SDA and then having a rising and a falling edge of the clock while holding that bit steady. So I2C is sort of a latch-based system as opposed to a edge-based system when it comes to sampling the bits. So basically you have the start bit, and then the master, it would always be the master, is going to be driving the clock. So the master then sends 8 pulses of the clock to send address bits 6 down to 0, so most significant bit of the address first. There are 7 address bits that are sent most significant bit first, and then followed by the read-write flag. If read is 1, then it's a, or if that bit is 1, it's a read. If it's a 0, it's a write. And then there is a 9th pulse that the master sends, which allows the slave to take control over SDA and then register an acknowledgement, which it would by driving it low, or a not acknowledgement by leaving it high. And that makes sense, because if it's high, it might mean the slave, is dead, in which case there's no one to pull it down. And since the default state of the bus is 1 because of the pull-up resistor, then that's what would happen. The NAC would automatically be registered. So there are 9-bit slots for the SDA, the first 8 of which are driven by the master, and the 9th is driven by the slave. In the second half of the transaction, it is another 8 bits for data, which can then be driven by the slave or the master, depending on if it's a read or write. Master always sets the clock, though. The slave would be driving SDA if it were a read, or it would be the master if it were a write, and then the acknowledgement would then come from either the master or the slave, depending on it's a read or write. So if it's a read, it would be the master would be acknowledging, because it's acknowledging the data coming back from the slave, and if it's a write, then it would be the slave acknowledging receipt of the data that the master wishes to write. And then you have a stop bit, which is similar to the start bit, except in this case it's the clock rising edge followed by the SDA rising edge. Remember, so the start bit was the falling edge of SDA, falling edge of clock. Stop bit is the rising edge of clock, rising edge of SDA. So it's in reverse. Okay. All right. So here's an example I2C transaction. So in this case, it's shown here. The bus address is the upper 7 bits, followed by the read-write flag, and then the most significant bit is transferred first. So we have the start condition here, falling SDA, falling clock, and then we look at the address is going to be 1, 1, 1, 1, 0, 1. So 4 ones and a 0, 1, followed by the read-write flag is a 1. That means we are doing a read. The next bit slot here is the acknowledgement, which is pulled low. That means the slave did acknowledge. And then we're doing a read, so the slave is going to remain in control of SDA and send back a 0, 0, 0, 1, 1, 0, 0, 0. It's 8 bits. Sorry, did I count that wrong? Let's go back. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and then the word would start here. So that's 0, 0, 1, 1, 0, 0, 1, 0. I think that's, sorry, count that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 1, 2, 3, 4, 5, 6, 7, 8. Right. So the least significant bit of the data would be in this slot would be a 1, followed by the acknowledgement, which is the master acknowledging with a acknowledge because it's pulled low. And then the stop bit is the rising edge of the clock followed by the rising edge of the data. Now in this case they look like they're going up at the same time. So I'll have to double check that, but normally it would be the clock first and then the data next for the stop. Clock rises, data rises. So I may need to check how we're generating those. I may have to correct that in the lecture slides, and of course the exam should reflect the fix. Okay, so here's another one. So we have our start, and then we have now again, just to clarify here, you're not looking at the edges of the clocks for the data. You're looking at in this case the slave side would be capturing each of these address bits while the clock is high. So in this case 0, 1, 0, 0, that's 4 bits. 0, 1, 0, 0, that's another 4 bits, followed by the acknowledgement, which is good. Now in this case this is going to be a write, so this is going to be the master. After the acknowledgement, the master is going to send the data once to write, which is 0, 0, 1, 0, 1, 1, 1, 1, and then the acknowledgement here is at the end. Okay, so be prepared to be able to read these. I may ask you, based on this, I may say, well, who's got the SDA bus right here in this slot? Well, the answer there would be the master. Why? Well, because it's a write operation. But if it were read operation, it would be the slave in control. I may ask you if there's a NAC transmitted somewhere in this transaction. So make sure that you can read these waveforms. Okay, so that's actually the end. So the exam questions will all come from the slides. Will all come from the material shown in these slides. Just as a reminder, we're not going to ask any specific questions about the Atmel chip that we use in class. These are all conceptual. Make sure that you understand the bus protocols, the 3 bus protocols that we covered in class, and make sure as well that you understand bit twiddling, interrupts, and pulse with modulation. So those are the topics that we'll be covering. One final reminder, make sure you go to Blackboard and complete the survey for the course, which I will provide some pointers on how to get there in an email. So we'd appreciate your feedback from the course. So good luck, and if you have any questions, please don't hesitate to contact me or Charles or Philip. Thank you very much.